Hi everyone, it's a great pleasure to be here. Today I'm going to talk about an evolution of foundation models, in particular focusing on architecture. So I'm old enough and I've been here for a while. So I decided to initially I was suggested to talk about transformers, but I decided to give some more evolutionary perspective how these models and architectures have changed through time. And I'll not get into the introduction. I think you already seen this slide already, and also Razvan gave an introduction. So I will directly jump into the presentation. So I'm pretty sure many of you are familiar with all these like large language models and like foundation models like Cloud, ChatGPT, and Gemini. They are chatbots that you can ask questions and interact with, or like have conversations with them. So there's like typical belief that they are like these like magical beasts that no one really understands, no one really knows how they work, and just like a pure black box. And the goal of this presentation is basically partially focusing on to kind of like bust that myth and like to explain you basically they are just like simple mathematical operations that are designed, architectures that are designed by people and trained on large amounts of data. And in general, like I talk about this like foundation models, like so you can see these foundation models as these like giant massive data regurgitators. So you can imagine them taking any forms of data as an input in different modalities like text, image, or video, and they can output like in principle different formats of data or modality of data, for example, again, like audio, images, or video. And like the kind of like in the core, there are different types of architectures people tend to use. Like the most popular one these days are the transformers. So I'll be mostly focusing on the transformers in this presentation. So if you look into this slide, you can see some of the models and how they kind of like change or like throughout different years. And in 2024, I didn't put any because like I could just like make just one big slide with just the names of the models and different foundation models just came this year. So like the progress in this field is immense and incredible, and there's like new models are coming up each day. So one of the main secret sauce of these like modern day foundation models is the autoregressive modeling of the sequences. During the autoregressive training of a large language model, let's say, the model is trained to predict the next word in a sequence based on the past history or the tokens that it already has predicted in the past in its context. So the kind of like the math is very simple. You can rewrite this like joint probability of like the tokens in the sequence by using the chain rule. So it basically multiplication of like you end up having multiplication of like bunch of like conditional probabilities. Given the current token, predicting the current token or the next token given the history basically. And so one obvious way of like training language model is the counting based approaches. So you can count the number of like occurrences of a token given its context. And this has been done in the past a lot in statistical machine learning, statistical NLP literature. However, this has been very difficult to scale and it has been quite inefficient. Thus, in practice, we usually use like parametric models, like neural networks, like to predict this joint probability. And like for these neural network architectures, you can use recurrent neural networks or like as I will talk like these days, people tend to use more like transformer type of architectures due to their scalability. In principle, this autoregressive modeling is very appealing because theoretically speaking, you can represent any distribution over a sequence of tokens using this like very simple rule by training an X token predictor, simulating the chain rule of probability. So I talked about autoregressive modeling. One core concept in autoregressive modeling is the teacher forcing. teacher forcing is a technique in training recurrent neural networks and transformers in general, or any sequence models in an autoregressive fashion. So during the training, the model's output is replaced with the actual output from the training data or the ground truth data for the next time step. So there are several reasons to do that. First of all, this gives you consistency with the maximum likelihood training, and also kind of like it ensures the faster convergence and stability. And also by using this and transformers, which I'll get into later on, it enables fast parallelism during training as well. So in the beginning, there were different components like recurrent neural networks. So you can think each different, you can think like you have like bunch of like Lego blocks, like let's say recurrent neural networks, self-attention, cross-attention, position encoding MLPs, and different components. And the goal, like the goal of the architecture designer these days is basically which components to bring together and put them together. And in this lecture, I will focus on mainly building a transformer, and I'll explain you which components you would use and why and how they work as well. And but like before that, like one kind of like fundamental architectural design was like recurrent neural networks. Basically, these models are similar to feed-forward neural network, but like you do unroll them like through the time. So you do share weights across different time steps, and basically the goal is basically given the previous hidden state, which is ht minus 1, and the current input, like to predict a new latent state, and then from that, like you do a kind of like softmax to predict the next token, for example. And you can do recursively, and this enables like efficiency and as well as like kind of like weight sharing and as well. And then you can just like model the whole sequence together. And in the end, like we train this with negative log likelihood loss function. So basically, you can see the RNNs as a latent state approach, in a way that like you have this like HT, hidden state, that basically summarizes the whole past input up to time t. And there are some pros and cons as well. Potentially you get this like infinite context with this like by compressing the whole past history within a just like small hidden state vector. And you get like faster inference because like you just need to keep a hidden state in the memory, but like also like there are cons like kind of like then you need to use an algorithm called backpropagation through time, which can be inefficient to train and like kind of like hard to parallelize, but also it introduces a long compute path between the history and also the current time, which can yield into vanishing or exploding gradient problems. And then, like after this, like these RNN models initially introduced in early 90s, late 80s, but like then in like late 90s and early 2000s, like there is this like new RNN architecture called LSTM was introduced. The main innovation in LSTM is the introduction of the gates, which like prevented the vanishing and exploding gradient problems. But like still the other issues that I mentioned still currently are still there. There are new approaches called like state space models and XLSTM type of architectures, which I think like Razvan will discuss more into it, that try to address these problems, but I'll be focusing mostly on transformer side here. And then like one of the most convincing application of this like RNN type of architectures have been, especially in language, have been this encoder-decoder structures. And basically, it was initially used for translation, but you can basically, using this architecture, any input sequence, map any input sequence to any target sequence, basically, that you like to associate with. And like the idea is very simple. You have this like encoder neural network that takes the input sequence, and just like since as I mentioned, the state of the RNN is basically a latent state vector that compresses the input sequence. You can use this like state vector to map the input, so to summarize the input sequence and then map into the other sequence, basically. So what you end up doing is very simple. You just like run this RNN on the input sequence, and then you take the last hidden state that summarizes the whole input sequence, and you have another decoder RNN that takes in this like last state vector, which is a summary, and then try to decode in the target. And kind of like the architecture is very simple and very general. You can imagine using here a transformer instead of LSTM or RNN as well. So one big innovation happened, like that also enabled transformers is basically the introduction of attention mechanism, especially in deep learning. It was initially introduced like more or less around the same time by Alex Graves and also Kyun Cho and Dima Badano at Mila. And attention in deep neural networks generally refers to any mechanism where individual states are weighted and then recombined together. So it involves two different mechanisms, basically. The matching mechanism that often involves like basically computing a score using some similarity metric that you defined. And then using those scores, you aggregate the state vectors, for example. This involves like weighted sum of the values using the weights computed during the matching. Sometimes people refer this as temporal mixing as well. So those two components are very important here. And so one big important innovation here is basically attention-based decoding that was introduced by Badan et al. In 2015. So the idea is very simple. They were looking into translation task. You have the input source language and sentence, and you try to translate into, for example, English to Polish, let's say. You get the sentence in English, and you just like feed into an LSTM. And then you have this like, you try to decode in the Polish, and like there's this intermediate attention mechanism that just like try to do alignment between the source and the target language in some sense. And the way it works, basically, you fit this input source sentence into a kind of like RNN, and then you just like compute this like scores that I mentioned earlier by using a matching function, and then you just normalize it to be able to get a distribution over the inputs using a softmax, and then you just like do temporal mixing or aggregation that I was mentioning before, and like you do the weighted sum using the scores assigned over the input states, and then like before feeding this vector into the decoder's RNN, they also apply a nonlinear transformation as well, using a simple MLP. And so this attention mechanism that I mentioned then introduced us like to this architecture called transformers that I've been mentioning about, and it caused like the Cambrian explosion of different foundation models, basically. And so instead of covering the detail, so basically this transformer architecture basically constitutes the basic backbone of all the foundation models that we know more or less nowadays, basically. So how it works? So one core concept here is basically self-attention operation. So here there are three different basically tensors here, K, Q, and V. So the Q is basically query, K corresponds to key, and the V corresponds to value. And like kind of like the names might be a bit confusing, but it's originating from, I think, inspired from the information retrieval systems, because most of the people that worked on the initial paper was actually working on the search and recommendation systems at Google at the time. So basically, this is more or less like analog to key, query, and values in retrieval systems. So you can think about like going to YouTube, writing a query to search for a specific video, and then like to be able to get the video that you want, like you match it with different videos which corresponds to keys, and then you do a search, and then you aggregate this search across the values, basically. And the way in self-attention mechanism it works, basically, you just like do the dot product between the queries and the keys, and this gives a similarity, which actually this is a scale dot product, which is normalized by square root of dk to be able to make the training more stable. And then we apply a softmax to be able to get the attention weights, and then we aggregate over values. And so again, to get into more details, so you first multiply the queries with the keys for every time steps. And let me remind you that like Q here is basically, and K are basically T by D matrices. Then after multiplying the Q and K transpose, then we apply, so we got a T by T matrix here, which is called like attention matrix sometimes. And then we do row-wise normalization on this matrix. And then we just like multiply with these values, which is also a T by D. So like there are some properties, interesting properties of this self-attention. So one of them is like basically they are invariant to different temporal permutations over basically Q, K, and V. And they allow all-to-all influence between Q, K, and V. And this also kind of like the computational cost here will be T square for the computing the attention weight, and plus like TD for the aggregation or the temporal mixing operation. And so there's also another concept which is like cross attention. You can see this as like being applied, for example, if you are in like, if you have like two different inputs for two different sequences. For example, in sequence-to-sequence models, like machine translation or like multimodal models. So in this case, basically, you can see like Q is like basically encoded from a different input from K and V. So like the idea with Q is basically it kind of like tries to answer the question of like where is this particular input, and then like the question of what is being answered by using the K and V vectors. So then we get the var question, and then we have the K, and then we just like do dot product between K and Q, and we apply softmax, we get the attention, and then we just like do aggregation. So the main difference here is basically Q and KV are coming from different inputs. But this is quite important, as I mentioned, for applications like translation or like where your inputs basically, you try to map a different sequence into a different sequence, basically. And so if you look into the transformer, basically, the attention operation is basically, self-attention operation is coming in the input side. And then after applying this, like it might look complicated, but like actually it's quite simple once you get used to it. Like basically you apply self-attention, and then I mentioned like there are normalization blocks. So you apply a kind of like residual connection from the input after self-attention, and then you do layer norm on top of that, and then another MLP with residual connection, and then another layer norm. So like this might look complicated, and the structure may look arbitrary, but initially I was really confused. Where are all these different components are coming from, and how do they decide this structure, right? Because like at the time, no one really had anything like that. But it turned out after talking to the authors, like they did very large search, and they did run a very big architecture search across different architectures and did lots of ablations, and they came up with this architecture. But then we know that why it helps. Like we know that residual connections help with the information flow, and also normalization helps with optimization as well. So in general, there are certain reasons why transformers are quite popular these days as a sequence model. Basically, basically one big important aspect of it is basically scalability, because unlike RNNs, basically you can, during the training, you can train the whole thing in parallel, unroll the whole model in parallel. You don't need to unroll step by step. And so it's easier to scale and it's easier to parallelize. And also, unlike convolutional neural network, you get the full receptive field. So you have access to the whole past data immediately. And also, unlike convolutional neural networks, the mixing over time doesn't increase the parameter count either. On the other hand, like, there are some potential cons, like, for example, all outputs like depend on all the inputs potentially, and there is no specific ordering of the data, which I'll mention that, like, there are ways to address those issues. And also another con potential is like the inference can be expensive, but again, there are ways to address that as well. So one important thing is basically to address the problem with the causal dependencies, namely to prevent the model putting attention over the tokens in the future. We can construct a mask matrix that we would apply by subtracting from the logits of the softmax. The way we would construct the mask matrix is quite simple. We just like initialize the lower diagonal of this mask matrix to 0, including the diagonals as well, and the upper diagonal to infinity. And by subtracting this from the logits, basically the attention logits of the attention weights, we basically make sure that the weights assigned in the future are exactly 0. So even though technically it's possible to construct our attention so that like we will not compute the attention over the future, but like in parallel, this is easier to implement on GPUs and easier to parallelize on GPUs as well. So that's the most common way of like getting the causal, temporal causality in transformers. And unlike sequential algorithms like other sequence models like RNNs, LSTMs, or SSMs, the transformers don't have an implicit mechanism built in to capture the relative positions of words in this sequence. This is important because the words provides, distance between words provides crucial contextual information. So this is where the positional encoder actually steps in. Positional encoder is not actually part of the architecture. It's actually part of pre-processing, you can see. But like the position encoding vector is generated to be the same size often as the embedding vector of each word, and the position encoding is typically added into the embedding vector. This pattern that is injected into the embedding matrix basically allows us, embedding vector allows the algorithm to learn this spatial or temporal information about the input ordering. So one of the most common way or initial positional encoding mechanism that was introduced was called absolute positional encoding. This was introduced in the original transformer paper. So basically you construct this, like, as I mentioned, additive positional vector, matrix, which is a bunch of like signs with different varying phases. And then like the goal of this, like kind of like the position encoding vector using signs and is basically to model some form of like basically binary vector that just like, that basically tell us the information about the position of the input token basically for a specific position. So as I mentioned, this positional encoding corresponds to sinusoid of different wavelengths across like different dimensions, and it usually goes from like 2 pi to 20,000 pi. This kind of like the numbers were selected in the original paper, but like typically you can adjust like if you are going for a longer sequence as well. But like the main goal here, as I mentioned, is just like to simulate something like binary encoding for positions using sinusoids. So now let's take a bit more functional viewpoint on the transformers. So like typically the input is coming from batch and with D model and length, and the output is like similarly has batch and D model and size of length. Typically the typical process is basically you just like go iterate over each one of these samples one by one in the sequence. So you start with like the first example in your batch, and then you just like get embedded. After tokenizing, you first like tokenize it so that like you map each one of these like words into a single integer tokens that the transformer can understand and interpret. And then this gives you a kind of like sequence of certain size, certain length. And then you embed these like tokens. So then you get like the model by length matrix. And then you start applying transformer layers on each one of these input embeddings. And then eventually you get the loss function. Though that's inefficient, and you potentially waste a lot of memory in your device. So like, and with like GPUs, modern day GPUs or TPUs, we have plenty of RAM. So one kind of like efficient kind of like way of like making use of that is basically by batching the operations. So you just like add an additional batch dimension to each one of these like different matrices, and you get a 3D tensor, for example, and then you process them in parallel. And so like that's, the embeddings are usually not very compute intensive. The majority of computation, the most compute intensive part is the transformer layers. And to improve the transformer computations on, and as well as like different aspects of the architecture, there have been several recent advances since the original transformer paper, so I'll go briefly some of them. And the first one is basically the introduction of like rotary positional encoding, which makes use of like rotation matrices. So in this slide, I just like show a rotation matrix in 2D, but in general, that rotation matrix is a matrix that is used to perform a rotation in the Euclidean space over a vector. So basically you can, in 2D, you can see of like, imagine a rotation matrix is rotating a point in a plane around the origin. And so the rotary position encoding initially introduced by Su et al. In 2021, encodes the absolute position with a random matrix, rotation matrix, and multiplies the key and the value matrices every attention layer to inject this positional information at every layer and at every time step as well. In general, so we will be working with like high dimensional vectors with foundation models. So for ROP, we need to generalize this rotation matrix to higher dimensional, higher dimensions than 2D. So the ROP divides the D-dimensional space into 2D divided by 2 subspaces to construct a rotation matrix of size D by D for token at every position I, basically. So this is the rotation matrix they use in the paper. Then, then you just like, if you do Q and K, or the matching operation in self-attention mechanism, then this will be the equation that you would be getting. So, so in a way, like one difference you can see, and one novel aspect of the ROP is basically, as opposed to the absolute position encoding or relative position encoding, the position information is injected into the embedding vector or the vector in a multiplicative sense basically. So like in a way, like one claim is basically this makes it more difficult for the model to ignore the position information, because it's easier to ignore if you just like inject it in a additive way. And it's just like apply, so we constructed this rotation matrix in D dimension. So we just like rotate the word vector or the input vector at every time step. So you can imagine like having a clock just like ticks every different token, and it rotates along the origin. So here, like the angle of rotation is proportional to the word's position at a position in the sentence. For example, the word vector is rotated by theta for the first position and 2 theta for the second position, and so on. So like there are two kind of like motivation that came with it. Like one of them is basic stability of the vectors. And like kind of like, as I mentioned, like it makes it harder to ignore the kind of like position information. And also, this also preserves the relative position. For example, if you say a word pig and the dog in two different contexts, like with kind of like same number of like tokens different between them, they will have like same position encoding across different contexts. And yeah. Yeah, so that's a good question. So it works strictly better in practice as well.
Can you also repeat the question?
Okay, so the question was like, does it also work better in practice or not? Yes, indeed, it works better in practice, and most of the novel or recent models like Gemma, Llama 3, they all use raw positional encoding. So there is like, it's not free lunch. So like one issue that people are trying to address is like generalization to longer lengths, because like if you use raw positional encoding, it becomes harder to generalize the sequences of length longer than the ones you have seen during the training. Because like this order information, position information is strictly fixed during the training. Another like initial transformer architecture or the block structure that I mentioned is using like the kind of like simple structure that not simple, but like the structure that I show in the image. So like as you can see, the layer norm is applied after the residual connection. So the one problem with this, like this was introduced in the original paper, but like later on, another paper that came out in 2021 that showed that this can be quite problematic in terms of like training stability-wise. One of the reasons is basically the expected norm of the gradients of the parameters near the output can get really large, and as a result, like training can be quite unstable. So the original paper, the Vaswani et al., to address this issue, the way they deal it, basically they use this warm-up schedule, but like so that like you start training the model with very small learning rate until warm-up, and then you just like increase it and then decay it again. But like even when you use warm-up, it can still cause instability. So these days, there is this like pre-layer norm architecture that most people tend to use, and like most of the recent architectures like Llama 3, Gemma, and potentially others that are closed as well are using this pre-layer norm architecture, where you actually apply, instead of like applying the layer norm in the output after the residual connection, you apply it in the input into the attention, and also input into before the MLP in the output of the residual connection after the self-attention. And so like, and the paper from Xiong et al. In 2020 showed that actually this works much better in practice and much more stable to train as well. And so there is this like typical normalization mechanism that's being used in kind of like in the original transformers and still used in some of the other foundation models. It's called like layer norm. Basically, layer norm is a technique used to improve the training stability of deep neural networks by normalizing the outputs, normalizing the inputs of each layer. So it helps to stabilize the learning process and gives you faster convergence and potential better performance as well. The key idea is basically to normalize the input vectors so that like across the so that like it will have zero mean and like standard deviation of 1 across the feature dimension. And it's achieved by just like computing the mean across the features at every mini batch and then subtracting it from the features and then dividing by some scale that you compute again across the features, and then you learn this like additional scale parameter, which is denoted as G here, and shift operator, which is B. And like G and B are basically free parameters that are learned during the training. And these days, like layer norm in most of the new architectures like Gemma or Gemma or like Llama 3, they are replaced by this other normalization called RMS norm. And it's one nice thing is like it's much simpler and faster than layer norm, and it makes it easier to parallelize across multiple devices, and it's quite stable as well. And it has less parameters, so it's much more popular, and like it's also kind of like gives you more or less the same performance as layer norm. And the idea is very simple. You just like compute the root square mean across like the features, and then you divide your feature with that scale, and then you learn additional free parameters for the scale as well. And now like since the original transform architecture was using rectified linear units for the MLP layers, and people have been playing with like what activation should we use and which ones would work the best. And there are several that's being used right now that are very similar to each other. GU, glue or swish, and or like GELU are activation functions. So one common thing with all of these like different activation functions is that most of them don't get to 0 when your pre-activations becomes negative. So like you still get some gradient even if your pre-activations are negative. And this seems to help to stabilize the training and also helps the performance of the models. And again, like there have been several works like playing with the MLP structure. So this is one of the MLP structure that was used by recurrent Gemma Griffin model that we worked on, that I also helped with, and also recently with Gemma as well. Basically, you have this like gated architecture where you have like given the input, you have like 2 linear projection, and on one linear projection you apply GELO activation function, and then you have multiplicative interaction between those 2 streams, and then you apply another linear layer. So like this again like seems to be mostly empirical reasons, like seems to be, work more stable, and it also helps you to pack more flops into your basic feed for layers as well. So as well as like it makes it easier to parallelize and scale the model as well. And so like again like one thing that recently people started looking into is basically most of the time if you go for large scale, actually it turns out that you are more than 60% of your flops are actually in the MLP layers. So you are more compute bound in the MLP layers rather than the attention. So there have been like some recent works on basically improving the MLP layers of transformers by using different structured matrices. And in this particular work, we looked into several different ones, including Monarch, toplets, or like even block diagonal. But the funny thing is like the simplest thing that we work, actually, that we tried as a baseline, end up working the best. Basically, instead of using full rank weight matrices, if you end up using low rank weight matrices with very large outputs, and if you train it with a mechanism that we call the self-guided training, actually it even outperforms like dense matrices, and it's faster as well. And again, like, so I didn't get much earlier into multi-head attention, but transformers typically use multi-head attention, where basically instead of computing a single attention score for each part of the input sequence, we have like multi-head attention that uses basically multiple sets of attention weights, or as we call it as heads, and each head performs its own attention operation independently. However, like this can be quite inefficient and hard to scale. So these days, like there are these alternatives like called group query and multi-query attention that's being used a lot, especially to improve the training performance as well as to improve the inference as well. So basically what you end up doing in the group query is like you can organize the query heads into groups and apply the multi-head attention mechanism using just like key and values heads, like less number for each one of the group, instead of like for each query having one K and V heads, you only have K and V heads only for groups of like queries, and then this basically reduces significantly the key and value vectors and key and value heads that you would have. And in the multi-query is like you can go even more dramatic. You can just use one on a single Q and K key vector for the whole queries, and this can further improve the efficiency and speed as well. And another kind of like important aspect of these like transformers is something called KV cache. So without KV cache, with transformers, you would need to recompute the attention for all previous tokens at every decoding step, and this can be very inefficient. So by using KV cache, basically what you can do is like you can store and reuse the intermediate computation results for keys and values during the generation of the sequences. And this caching mechanism significantly improves the efficiency of the model. Especially, I mean, this is something that you would only use in the inference time. So like this improves the efficiency significantly in the inference, basically. And, but the KV cache can be a bottleneck as well, because like, especially if you are in multi-headed kind of like attention, using multi-head attention, then the KV cache, especially if the context gets very large, can become very large, and keeping the whole KV cache in the memory can be costly, both in terms of memory, but it can also cause like efficiency bottlenecks as well, because then you would have to transfer the KV cache from the HBM, host-based memory, from the GPU's memory into the compute core. And this can, the bandwidth between HBM and the KV cache, compute core is limited, so it can cause significant slowdowns, especially as the KV cache gets larger. So there are lots of like tricks people use to get over that, like for example, quantization, pruning mechanism that gets rid of like the unnecessary, basically redundant vectors. And page attention is another mechanism that is popular these days. And another kind of like way of like improving basically the attention mechanism is basically using something called local or like sliding window attention. So with attention, as I mentioned, like computing the full attention matrix can be quadratic in time. One way to kind of like improve that is basically by doing attention over the fixed local windows, and of like so you have this like sequence length L, let's say, and you have the window length W. As a result, instead of like having L square attention computation, you can reduce it to LW. And this seems to be much faster, both during the training and also inference time as well. And also it allows each position to attend only a fixed number of tokens in the past, and significantly improves the inference efficiency by reducing the cache size, KV cache size. And like the performance drop that you see usually in in the modern day transformers is not huge, and recent Gemma work basically, the way they overcome this like local window issue to increase the context, they interleave the full attention, the regular multi-query attention with the local sliding window attention. So you don't apply it every layer, you apply every other layer. And this gives you the, again, like full context, but also it's still very efficient compared to regular attention mechanisms. And recently there have been a lot of like resurgence of like hardware-aware algorithms. So one of the most prominent one is the flash attention. So flash attention is basically designed to improve the performance of the attention mechanisms in transformer models, and particularly for large language models. The way it works basically, the goal here is basically to maximize, so there's like this memory hierarchy in this like, in these hardwares. So like you have SRAM on GPU and HBM. HBM is DRAM, and SRAM is very close to the compute core, so it's much faster. And HBM is like slower and lower bandwidth as well. But like the problem is like you have abundant of HBM, host-based memory, whereas limited amount of SRAM. So the question here is basically, how can we best make use of this like SRAM as much as possible? And one really bright idea that the authors, Trido and others came up to address this problem is basically you can tile the attention operation into smaller blocks or smaller chunks that would fit actually in SRAM. So you just like split the attention computation into smaller blocks, load into SRAM, and then perform online softmax normalization in each block and in an online fashion, and then using the tiling, you can move between different memory levels. And this has speed up the attention mechanism for transformers, especially on GPUs, quite significantly, and has made a huge impact. And recently, there have been a lot of interest in how can we incorporate the hardware design and architecture design together to be able to make best use of both, basically, so that like, and also make these models and architectures more efficient as well. And again, scaling transformers. Now, like I will briefly, quickly talk about scaling these models. So the scaling transformers basically means like how to do efficiently lots of math modes in many machines in parallel. So this thing involves like both like distributing all the matrices across like different devices involved in basically, and then also another constraint we have is like we wanted to minimize the communication between different devices as well. So if you look at the models like and the history of the architectures, we can see that like machine learning models, the parameter counts doubles every almost like 18 months in like in 1950s. But like these days, like if you look at the last like from 2018 to 2021, you can see that instead of like every 2 years, you see the parameters of the models doubling. It's only 4 to 8 months, basically. So scaling has been huge part of this like success of these models, both in terms of like the data, but also parameter counts. So there was this like really interesting insight from Sarah Hooker. She published this paper, something that she called as hardware lottery. So what she claimed in this paper is like, it's not the elegance or like kind of like how mathematically a method is kind of like formulated or like, that's not what it determines the success of a machine learning approach. What determines is basically if a given approach is easy to scale with the current hardware generations. So this is called hardware lottery, and currently transformers are winning the hardware lottery, but like there are lots of other alternative architectures coming that we hope like we might see more alternatives as well. And so one mechanism to scale these models is called pipeline parallelism. So basically, this is one of the simplest approach that you can imagine. So in this approach, the model is split into multiple stages, and each stage, for example, this can be each layer of the transformers is assigned to a different device, and the output of one stage is fed into the next stage. If you are, for example, pipelining or 8 layers of MLP or across 8 devices, you basically place each one of the layers in one device, one specific GPU, and then the output of the first layer of the MLP will go on the first device, will go into the second layer on the second device. So this is called like, this enables concurrency across like computation of like different parts of the model while processing the input. And this can bring some bottlenecks as well, because like in the figure you can see the bubble, because so one of the device, like while they kind of like process the input, the other devices might end up like waiting for the output of the earlier stage. And this can cause like the concurrency issues, and as a result, there are other methods that's being also used, like to be able to enable more efficient use of like model parallelism. So one of them is like Megatron tensor parallelism. So it's basically looks into how to kind of like shard the different tensors in the model more efficiently across like multiple different devices to reduce the communication bottleneck across different devices. Because with pipeline parallelism, you need to communicate between different devices at every layer. And so one simple way you can think of this working is basically the weights of the model's layers are divided into smaller chunks or shards, as one would call, and each shard is assigned to a different GPU. So this means that instead of GPU holding the whole complete copy of the model of the weights, each GPU only has the smaller part of the weights or the tensors. And like, for example, one way you can think of you have like 2 layers of MLP. The first weight matrix you can shard across the columns, and the second matrix you can shard across the rows. And like you can store those each columns and each row kind of like sharded matrices on different devices, but you make sure that the communication only happens at the end, because like you can shard it. If you shard columns and then rows and the columns and rows, you can basically ensure that like to be able to do the local computation, you don't need to communicate between different devices until the end of computation path. And so Megatron basically was proposed in 2019 to address this issue. So like in the original paper, they introduced this like fake F and G operation. F is identity in the forward probe, and basically all reduced. That means like it's a kind of like communication across like different devices to synchronize between them. And like there's this G in the output that's like basically all reduced in the forward probe. Like so you only in the forward probe, like you only communicate between devices across devices at the end, and in the backward pass only in the beginning when you do the back propagation on the inputs basically. And and this has been very successful. Basically, Megatron has been used like for training probably most of the large language models that we are using these days. And another approach is basically Zero. Zero basically enables data replicas to store parts of the model that's not currently in use. So it helps you to kind of like basically address some of the memory bottleneck and also efficiency issues in large-scale deep learning training. So like, and there are different stages in Zero. So like, depending on which stages that you choose, like you can trade off between memory and the communication cost, basically. So as opposed to Megatron, this also allows you to basically shard across, shard the optimization optimizer states as well as gradients, and as well as parameters. So basically, in the stage 1, you partition the optimizer state, across like multiple GPUs, and this has like very low memory usage, but like this has like reduces the memory usage, but like still, and reduces the communication costs, but like it can just like, and also reduces the memory usage, but the communication can still be a bottleneck. And as you go to the higher stages, basically, then you can lower the memory usage, but increase the communication cost. And finally, like one last point I'll make is basically scaling laws have been very impactful to find the hyperparameters of these models. So like, for example, the goals of the scaling law curves that we have been doing for training LLMs is basically like transfer questions, like for example, if I had like 10,000 more data points, what would change? Or like if I had 10,000 larger models, larger number of parameters, how would the validation loss change? So it basically involves like doing lots of experiments on smaller scale and doing extrapolations to the larger scale, for example, both in the data and the parameter. Yeah?
Small question about the zero.
Yeah.
In the table, it seems like the communication overhead doesn't grow. Why would it not grow? Because you kind of looks like you get for free this.
So the goal here is basically more reduce the memory consumption. So actually the communication cost can increase because like we compare the baseline here. Baseline is just like single model trained on a single device, and then as you kind of like reduce the reduce the memory consumption, you increase the communication cost here. Is the same with the baseline. It doesn't change, but like as you kind of like reduce the memory consumption, it introduces the, but we can discuss more offline if you want. I didn't get into as much details. Yeah. And like there have been very important works on basic the scaling laws. One of them is Chinchilla laws, basically. Published by Hoffman et al. In 2022. So the kind of like, they went up to 70 billion parameters with 1.4 trillion tokens. And the goal here is basically to address some of the open questions that was in the original Kaplan et al. 2019 paper that was left open for the scaling laws. So original paper was like assuming fixed hyperparameters and especially the fixed learning rate sketches. So this paper also extended the changing hyperparameters. And the main goal here with this like scaling laws that we try to address is basically given a fixed compute, how to trade off like the parameters and the data basically. Okay, I'll wrap up here, and I'd like to thank all the organizers, Razvan and Viorica and the rest of the team and Petar, and also, all my collaborators as well. Thank you. So the question is basically, are we saturating the improvements in the transformer architecture innovations, or is it only about engineering these days? So that's a good question. So of course, like as the new hardwares come up, like there is more like hardware level optimization that needs to be done, and it mostly requires both understanding the architectures and innovating in the architectures to be able to kind of like make them more suitable for the new generation of hardwares. So there is like still some interesting questions in the intersection between engineering and also different architectural innovation. But also I think like the current belief is like the transformers solve all the problem, but there are still lots of, I think, things to address. They work very well for this like generative modeling, but there is lots of questions that needs to be addressed around different inductive biases for different data types, like that's not necessarily language or images, like graph and other structures, but also around the efficiency and inference as well, for example. It's a huge problem. And there are lots of like methods and architectural innovations happening. Or like the position encoding is another simple one that there is a lot to be done.
I have a question about the block and how do the authors find the intuition between the rank up and rank down feed forward, and did you further scale it to gated feed forward? I mean, what were the intuitions between those two and how did they get to that part?
So you mean the transformer block?
In the transformer block, the rank up and rank down, the feed forward.
Okay, yeah. So it was a work that I was. So the question is basically if you use, sorry, keep forgetting. If you use like structured matrices for the transformer MLPs, the authors found that low rank matrices work the best, and in terms of efficiency. So the question was like, how do they come up with that structure? So I was part of the project, and like, so the kind of like the reason we looked into is basically we were interested in using in general structured matrices, not specifically low rank. Low rank matrix is one type of like structured matrices. So we tried like lots of different variations that we thought might work better, like monarch and kind of like toplets or like block diagonal matrices. But it turned out actually they introduced different inductive biases, although these matrices work very well. That introduce local structure for images. For language, actually, low rank matrix was like empirically the one that worked the best, and like it decreased. So the kind of like one thing that we find is basically you can decrease number of parameters by representing the matrix in low rank, but you can also increase the width of the network as well. So this width, increasing the width actually while reducing the number of parameters actually seemed to be improving the generalization of the model. And for some reason it generalized better even on downstream tasks as well. Yeah. Yeah. Mm-hmm. Yeah. Yeah, exactly.
That's the intuition between these rotations per the way.
Yeah. Like, or you can think of like kind of like rotating the vector so that it represents like a clock basically. Each position, it kind of like represents a specific point on the kind of like basic on the disk basically in disk. Yeah, exactly. On the sphere, high dimension. Sorry, I couldn't hear. Can you repeat?
Maybe I can repeat it.
Yeah.
Maybe I can repeat it in the mic. So I think the question is if there is an easy way to estimate the size of the model given the size of the data. So if you have a data set, like how do you know what size model should you run for that?
Right. That's a good question. So like that's basically scaling laws, kind of like the last part of the related to presentation that I just like showed. I didn't get into too much details, but like if you are using a specific architectures, if there is an existing scaling laws, basically that are being done, you can try to kind of like use the same laws. Otherwise, like what you can do, you just like try to kind of like run lots of experiments at different scales and see how the performance of the model changes. And then you can, depending on the compute budget or the data budget that you have, you can trade off between the compute or the data and like decide to achieve the kind of like the validation loss or the performance that you want to reach what's the kind of like, and given a specific number of data, what's the kind of like the size of the model that you try to train. And then you can do these experiments on small scales and try to kind of like extrapolate it basically to the larger scale to see when you would reach the loss that you want to achieve, for example. So the short answer is like scaling loss, basically. It seems to be a good way of doing that. So the estimating the scaling, sorry, I'm not sure.
Sorry, maybe I can jump in. So I guess the point is, if you have a compute budget, because scaling laws only make sense then, if you have a compute budget, then the scaling law is a curve that tells you, for that compute budget, for that amount of data, what is the model size. So you do that at very small scale, so that's going to be a line, and you extrapolate it, and then you just look at that line where it intersects. But that assumes you have a fixed compute budget. If you don't have a fixed compute budget, then the bigger the better, like there's no limit. But if you have a compute budget, then you just look at that line, and that would say what model to use. Any other questions?
Did I? I think like that was the starting point of the Chinchilla papers. That's my understanding. So initially they started to try to use the same scaling laws from the original OpenAI paper introduced by Kaplan et al. And they kind of like realized that actually it's not as optimal as they thought, because like the original assumption in the paper was that like that like the number of the hyperparameters are fixed and the learning rate schedule is fixed as well. And so like then they try to fix this, but like personally I did encounter that as well. So like especially kind of like the scaling laws that you kind of like get can be biased with the number of experiments that you run and like how you extrapolate as well. And so it can be quite kind of like, it requires like very quite careful investigation of how to extrapolate and how many experiments to run and like at what sizes and the number of data points that you have. That basically very important to be able to extrapolate carefully.
Okay, the last question there.
Also, I guess continuing this conversation, which should also be task specific, right?
Yes, that's correct. That's correct. Like, yeah.
Very quick one. So for like, I don't know, a year maybe or 2 years now, we're observing that most like open source models, they're kind of, like, for example, Llama, like the biggest open source Llama models are around 7 TB. There's some other models that are like still like, let's say between, well, around that and maybe 300 B. Why aren't we seeing like much larger models? What's the limiting factor?
So I think like the main limiting factor is there basically. So the first, like the larger number of parameters doesn't always like need to mean that better performance. It depends on the number of data points as well. And the second thing is like the inference, because like as you increase the model size, then it makes it harder to deploy them into the real world use cases. And usually in practice actually, smaller but more efficient models are kind of like maybe more valuable at the moment.